Good morning. Welcome to lecture 5 on unit 1, and in this lecture we will be talking about degree of freedoms and bandwidth. So, let us first look as what is the outline of the lecture, and in today's lecture we will first complete what we left from the orthogonal expansion. We will be talking about discrete time Fourier transforms and how they can be used to get what is known as T spaced sinc weighted sinusoid expansion. Then we will look into what is this degree of freedoms, then we will look at the bandwidth of signals and systems, and then we will learn about channel capacity. So, let us first start by finishing this idea of orthogonal expansion. So, first of all, let us write the double sum expansion built using TTFT, and this expression follows exactly as what we derived in the case of double sum expansion that was built using Fourier series. So, first let me write the expression. So, we will have BKM multiplied by e to the power minus j pi by w kf into rect f by 2 w minus m. So, what we are saying in here is, again we use these as orthogonal functions, and using these orthogonal functions we can carry out a double sum expansion by using the ideas that we developed using DTFTs. So, what does this say is, let us assume that I have a signal, and this is let us say the spectrum of the signal, and if I again divide these spectrum into segments, and I can have different segments, and let us assume that each segment is of bandwidth 2 w. So, while considering a segment at a time, I can obtain these coefficients for these segments. So, BKM are the coefficients of the mth segment of the signal whose spectrum is XF, and using these BKMs and using these orthogonal functions we can carry out a double sum expansion. So, this is exactly same as was in the case of double sum expansion of Fourier series, only we have now a different orthogonal function, everything else remains same. Okay. So, again you can think about this as XF is expressed by using some coefficients into some orthogonal functions, and now we see, because we are using double sum, we have the coefficient with 2 subscripts. This m subscript tells me that these BKM are the coefficients corresponding to the mth segment, and similarly phi km tells me that this is the orthogonal function corresponding to the mth segment. So, let me write this phi km orthogonal functions again. Okay. And if we want now to get this BKM, obtaining these BKM is easy, it is safe. You can get these BKMs by taking the inner product of XF with these phi kms, these orthogonal functions, and of course dividing by the energy of these functions. You can prove that the energy of these functions is 2 w. Energy of the functions in the case of Fourier series was T, and we know that because T is getting mapped to 2 w, the energy of these orthogonal functions can be thought as 2 w. Okay. Let us again now try to do what we did in the case of Fourier series. So, let us start by taking the inverse Fourier transform of this expression. So, let us start with this. So, we have to take the inverse Fourier transform of this function, and again using the ideas from Fourier word, we know that the inverse Fourier transform of a rectangular function is a sinc function. Fourier transform of shifted rectangular function can be obtained by multiplying a sinc function with a rotating complex exponential, and this complex exponential will contain this factor of 2 mw corresponding to this frequency shift of m2w. And again, if we want to find out what is the inverse Fourier transform of this shifted rectangular pulse multiplied or shifted rectangular function multiplied by this rotating complex exponential, it can simply be obtained by changing this t to t minus k by 2w. So, wherever you have t here, you just have to shift it by this factor of k by 2w. And thus, if you want to find the inverse Fourier transform of this, it can simply be obtained like this. So, what we have said is we are starting with these functions, and we are taking the inverse Fourier transform of this, and we have obtained the inverse Fourier transform of these orthogonal functions as 2w sinc 2w t minus k multiplied by e to the power j 2 pi m 2w t. And what are these BKMs? Can be obtained without doing anything difficult? Yes, so by just applying mind to what these BKMs could be, we can easily obtain them. For example, we have seen previously that BKs, they were the sample xkts by 2w. So, what are these BKMs should be? So, let us go back to that picture again. So, what we are doing herein, we have a signals, a spectrum. We are taking a segment of this spectrum. The segment exists for a duration of 2w. This is the mth segment. If I take the inverse Fourier transform of this segment, mth segment, I would get a time domain signal which we call as xmt. So, these BKMs are nothing but they are the samples corresponding to this xmt. So, I have to take the samples of these xmt and divided by 2w. So, this is just obtained by using our mind based on what these BKs were. So, substituting this obtained value of BKM into this expression, what we will get is xt is summation mk xmkts by 2w into 2w sinc t by ts minus k e to the power j 2 pi m t by ts. So, what we have done more is, so we have actually done two things. First, we have substituted the values of these coefficients, and then we have also substituted 2w as 1 by ts. Okay. So, we have also substituted 2w as 1 by ts. and we get now a double sum orthogonal expansion of the signal x t using the ideas of d t f t. And what is this? This goes in the literature by the name of T spaced sinc weighted sinusoid expansion. Okay. So, these sinusoids are weighted by these sinks, and these sinks are T spaced sinks, and hence the name T spaced sinc weighted sinusoid expansion. Okay. So, let us revise what we have seen so far. So, first we develop single sum orthogonal expansion. For example, we have looked into Fourier series. In Fourier series, we expand a signal in terms of these truncated sinusoids. Then we have this DTFT, which is time frequency dual of this Fourier series. If I take the inverse Fourier transform of this DTFT, I get to this sampling theorem. And then we also looked into double sum orthogonal expansion. So, from the idea of Fourier series, we ended up with this T space truncated sinusoids, and using the ideas of DTFT, we obtained this T space sinc weighted sinusoid expansions. So, these are the kind of orthogonal expansions that we wind up in practice. Let us look into the next concept, and it is a very interesting concept, particularly for engineers. A lot of rule of thumbs are derived using this idea of degree of freedom. So, if I assume that x t is time limited signal and it is time limited to duration t naught, for example, I can assume that it spans from minus t naught by 2 to plus t naught by 2. And if I assume that x t is band limited to a bandwidth of w naught, the question is how many coefficients or how many numbers are required to represent this signal x t. And the number of coefficients that would be required to represent this signal x t is known as the degree of freedom of this signal x t. So, let us look at the number of coefficients that would be required, and it follows very simply from the ideas of sampling theorem that we have just seen. So, if a signal is of duration t naught, and we have already seen that we need to collect these samples of this signal at a duration of 1 by 2 w, if w is the bandwidth of the signal, then the number of coefficients that I need to have that would be sufficient for the representation of the signal can be simply obtained by dividing the total duration by the period at which samples needed to be collected, and this number would be 2 w naught t naught. So, this is typically the degree of freedom of a signal. And why is this factor 2 popping up here is because of the notations and the way in which we define the duration of a signal in time domain and the duration of a signal in bandwidth domain. When we define the duration of a signal in bandwidth domain, we only define for the positive side of the spectrum, whereas when we define the duration of a signal in time domain, we take into consideration the total duration of the signal. We can also interpret this degree of freedom in another way. So, if I have a signal x t and I want to store this signal into an array, and I have already said that this is important for signal processing ideas. You cannot store a CT signal, continuous time signal. You need to convert this signal into sequences, and so the question is, what is the length of this array that is required to store this signal? And again the length will correspond to 2W naught T naught. And what kind of numbers fill in here depends upon what kind of signal is xt. So, if xt is a real valued signal, these numbers are real numbers. So, for a real valued signal xt, which is time limited to a duration of T naught and bandwidth limited to a bandwidth of W naught, the number of real numbers that we require is 2W naught T naught. If xt is a complex valued signal, then the number of complex numbers that we require to represent the signal xt is again 2W naught T naught. So, that this looks easy and simple, is not it? But there is a mathematical intricacy that we have avoided so far in this discussion, and this mathematical intricacy is that time limited signals can never be frequency limited signal or bandwidth limited signal. And you must have seen this in signals and systems, that if you squeeze a signal in time domain, the signal squirts out in frequency domain. If you spread a signal in time domain, the signal gets squished in frequency domain, and this is because time and frequency are reciprocal spaces. So, making a signal time limited would make it bandwidth unlimited. There is this assumption that a signal is time limited and bandwidth limited at the same time does not hold. So, how do we get rid of this problem is the question. Moreover, we can see that practical signals will always be time limited. That means, if you want to transmit a signal, the duration of the signal can be only finite. You cannot transmit a signal from minus infinity to plus infinity, and also we can see that these practical signals will be band unlimited, and this follows from this Pali-Wiener theorem or condition, which says that for the practical realizability of the signals or systems, the integration of mod of ln mod h omega divided by 1 plus omega square should be finite. So, Pali-Wiener theorem says that this complicated integration should be finite for practically realizable signals or systems. In another word, it says that if, let us say, h omega, let us assume it is 0 between omega 1 and omega 2. So, between two frequencies omega 1 and omega 2, let us assume that this h omega is 0. If this h omega is 0 in this frequency range, mod of ln mod of h omega will be infinite in this frequency range, and hence this integration would become infinite. Hence, what we are saying is, if h omega is 0 for a continuous range of frequencies, this integration would become infinity and Pali-Wiener condition would not hold, and thus for Pali-Wiener condition to hold, h omega cannot be 0 for a continuous range of frequencies, and thus a signal can never be band limited. So, what we are saying is all practical signals need to be band unlimited and time limited. So, the question is, how then we talk about this degree of freedom, which was a nice idea that I can represent the signal by using these coefficients, these many number of coefficients. And the idea is simple. When we are saying that this can be represented using these many coefficients, what we are saying is whatever we are losing out does not matter for us. So, from practical sense, you would lose out energy when you do this conversion, but the loss in the energy is of no practical consideration, and from engineering sense this number makes sense. Okay. And so, one thing that we will see is what are the good examples of the signals that can be approximated as band limited signal. So, no signals or no systems will be band limited ideally, but we will investigate what are the good examples of signals or systems which can be approximated to be band limited signals or systems. Okay. But before all of this, let us now talk about the bandwidth of the signal, and before even talking about the bandwidth of the signal, let us talk about these two kinds of signals or systems, the baseband signals in systems or passband signals in systems. So, mathematically we can say a baseband signal or a system is a system whose spectrum is mostly concentrated at around DC, and a passband signal or a system is a system whose spectrum is mostly concentrated at around certain frequency Fc, and that is easy to understand. We can also understand this pictorially. So, this is the spectrum of the baseband signal or a system where most of the energy is concentrated at around DC or is confined in this range. For a passband, what we will see is most of the energy will be concentrated at around a higher frequency Fc. And these two kinds of signals and systems are important. We have already seen this picture of attenuation versus frequency profile of various kinds of channels, and here you see that optical fiber has a low attenuation for very high frequencies. So, optical fiber is a passband channel, coaxial cable is also a passband channel, twisted pair can be used both as passband or baseband channel. So, you can transmit digital data directly over twisted pair, and that is what is used in Ethernet LANs, or you can use discrete multitone modulation where you transmit the signal in form of passband signals. In case of wireless communication is mostly passband, because we know that if you can operate communication over higher frequencies, antenna size reduces, and so there is an incentive to have communication systems at higher frequencies. So, you can reduce the antenna size, and because we now want to make our devices smaller and smaller, passband communication is preferred in wireless systems. Also, we know from electrical world that the quality factor of electrical circuits is given by this omega naught by B, and because this quality factor is rather a constant quantity, it lives between hundreds to few hundreds. So, we can approximately treat this as constant. So, what we then can say is that this bandwidth will be proportional to omega naught, where omega naught is the frequency of operation. So, what we are saying is as the frequency of operation increases, bandwidth of the system also increases, and that is the second reason why we love this passband communication, because it has the possibility to offer higher bandwidth. Okay. So, after understanding about this baseband and passband communication systems, let us look at this idea of bandwidth itself. We have not yet talked about this bandwidth concisely. So, let us look into what is this bandwidth, and the definition of bandwidth is quite easy if the signal in consideration is band limited signal. For example, if the spectrum of a signal or mod of a spectrum of a signal is like this, we know that it is a band limited signal or it is a good approximation towards band limited signal. So, how do we define bandwidth? The one idea is just to look at the positive side of the spectrum, and if you just look at the positive side of the spectrum, bandwidth will be B. If you look at both positive and negative side of the spectrum, bandwidth will be 2B. We say this as one sided bandwidth and we say this as two sided bandwidth. And we know for real valued signals, because mod of HF is symmetric, one sided bandwidth is always going to be half of two sided bandwidth. Okay. However, for complex valued signals, we have mod of HF which is not symmetric. So, mod of HF might look something like this. Now, in this case, our good old rule that one sided bandwidth is half the two sided bandwidth does not hold. So, in literature, what is given or chosen as the definition of one sided bandwidth in the case of complex valued signals is you look at the total support, that means we consider both positive side of the spectrum and negative side of the spectrum. So, we get the total support as V1 plus V2 and divide this by 2. So, this is the definition of one sided bandwidth in case of complex valued signals. And as I have stated before, when we are just given bandwidth, by custom we consider bandwidth as one sided bandwidth. So, if nothing more has been specified about the bandwidth, whether the bandwidth is one sided or two sided bandwidth, it is a good bet to consider the bandwidth as one sided bandwidth. But another definition of bandwidth for complex valued signals can flow from this idea of equivalence between the real passband signal and complex baseband signal. So, we will see later on that a real passband signal has an equivalent representation in baseband domain, and this representation of a real passband signal in baseband domain is normally complex. And this complex value signals arise because of this equivalence between passband and baseband signals, because no signal can exist in reality as a complex signal. So, whenever we are saying complex valued signals, it is an analytical signal and it is a signal which models the behavior of a real passband signal. So, if we look at the bandwidth of this real passband signal, we have to look at this support. That means, we can look at only the positive side of frequencies if we are talking about the one sided bandwidth, and then for the complex baseband signal, the bandwidth should be considered by looking at both sides of the spectrum, because this length here or this duration here equals to the total duration in the case of complex baseband signal. And thus, from the equivalence point of view, the equivalence between the real passband signals and complex baseband signal, the bandwidth of a complex baseband signal can be considered as the total bandwidth. So, looking at V1 plus V2. Okay, so far it was easy, and let us now try to define bandwidth for band unlimited signals. So, when we are thinking about band unlimited signals, there are various definitions of bandwidth that we can think about. We will take all these 4 definitions one by one. So, we have fractional containment bandwidth, equivalent rectangular bandwidth, 3 dB bandwidth, and peak to first null bandwidth. So, let us start with the idea of fractional containment bandwidth. And the idea of fractional containment bandwidth is that we are interested in the range of frequencies for which a fraction of energy is contained. Okay. Let us look at this. Suppose we have a rectangular pulse. So, we denote this as rect t by t, and you know now that this goes from minus t by 2 to plus t by 2, and it takes an amplitude 1 between minus t by 2 to plus t by 2. And if I take its Fourier transform, I get a sinc pulse, and the expression for the sinc pulse is t sinc f t. And if I am interested in the energy of this pulses, I can use Parseval's theorem to either think about the energy in terms of a time domain signal x t, or in terms of frequency domain signal x f, like this. So, this equivalence follows from Parseval's theorem. Now, I can define bandwidth as B, for which this equality follows. Where the energy contained in the total support of 2B, that means if I carry out this integration between minus b to plus b, I get certain energy, and this energy should be some fraction times the total energy, and the total energy can be obtained like this. So, A is a fraction. So, the value of A will go from 0 to 1, and for this equality whatever the value of V we get, that is the bandwidth. Now, thinking about this total energy directly is little bit inconvenient, but we can think about this thing in terms of this, because these two are equivalent expressions from Parseval's theorem. Now, this is easier integration to do because x t is a rectangular function. So, it is 1 only between minus t by 2 to plus t by 2. So, I can simply go from minus t by 2 to plus t by 2, have 1 in here, and this would easily integrate to t. That means, I can think about the bandwidth by solving for this expression, and now let us try to simplify this bit more before you resort to computer to solve it. You cannot solve it by hands, it should be solved using computers, but let us simplify this little bit further by thinking about that this mod of x f is a symmetric function. So, rather than carrying out this integration, it would be nice or simpler to just carry out the integration between 0 to b and just multiply thing with 2. So, from this we have to solve for this expression. Substituting the value of mod of x f, we get and now we see that t cancels with 1 t, and finally what you have to solve for is this expression. So, a t has to come in here. Now, I can even simplify this further by changing the units of my universe. So, I can define a new universe in which I have changed my time scale. So, I am saying that my new time scale in my new universe, my time scale can be obtained by dividing the time by t. So, this t naught is the time scale in old horizon in this viewpoint, and this is the time scale that I would choose in a new universe. Let us use the word universe, it is better. And thus, the pulse which was of a duration t in the old universe becomes a pulse of duration 1 in the new universe, because in the new universe this is the time scale that I choose. And thus, I can simply replace this t with 1, and I can rather solve this equation because now my t is 1 in the new universe, and now I can find the value of B n. Because you have changed your time scale in the new universe, your bandwidth will also change in the new universe, and because time and bandwidth follows a reciprocal relation. So, your bandwidth in the new universe would be t times the bandwidth in the old universe. So, if you have to find bandwidth in the old universe, it is nothing but B n by t. So, I am saying is you can simply solve for this expression, get the band value of B n, which is the bandwidth in the new universe, and you can find out the bandwidth in the old universe in which we were interested by just dividing this bandwidth in the new universe by t, and you are done. These are certain tricks that you can use. You can anyway could have solved this equation directly, okay, in computer. Let me put out some values of bandwidth for values of A. So, if I choose A as 0.99, that means I want 99% of energy to be confined. My bandwidth turns out to be 10.2 by t, and if I choose A to be 0.9, the bandwidth that I need to have is 0.85 by t. So, based on what fraction of energy containment you want to have, the bandwidth requirement varies. Of course, bandwidth should be a function of t. Let us take the second definition of bandwidth, which is equivalent rectangular or noise equivalent bandwidth. Idea behind this definition is that if you have been given a particular mod of HF, let us think it like this. So, this is mod of HF that has been given to us. I can find the equivalent bandwidth of the system by thinking about putting a rectangular cap around this mod of HF, where this rectangular cap is centered around the peak value of this mod of HF. So, this is the peak value. So, this rectangular cap sits or is centered around this peak value, and this rectangular cap takes a total support of 2b, then the bandwidth is defined as the value of b for which the energy contained in this rectangular cap is the same as the energy contained in this HF. So, let us see what I mean with this. So, the energy contained in the rectangular cap would be nothing but, because rectangular cap goes from minus b to plus b, and the height of this rectangular cap is same as H max. So, this value H max, for simplicity let us assume that the peak value of this mod of HF happens at f equals to 0. So, this is also mod of H of 0. So, the magnitude of this is nothing but mod of H of 0, and the energy thus would be the square of the mod of H of 0 times df. This is the energy that would be contained in the rectangular cap, and the total energy that would be contained in HF can be evaluated using this expression. And because this quantity is independent of frequency, I can pull this out and I get this thing, and from here I can find the bandwidth. Let us try to do this for a sinc function, because we did the previous examples with sinc. Let us again consider a sinc pulse. So, remember the expression of sinc pulse is this, it is a Fourier transform of rect t by t. So, we have been using the same pulse for the comparison between the two definitions, and so if I plug this into this expression, again as I have said, finding this out directly will be very difficult. So, let us think this in term of this divided by 2 times H of 0. H of 0 here, the peak value of this would be t. So, this is 2 t square, and this, as we evaluated in the previous case, is nothing but t. So, this will evaluate to t. So, the bandwidth with this definition turns out to be 1 by 2 t. So, this is the equivalent rectangular bandwidth or noise equivalent bandwidth. Now, let us look at the third definition, that is 3 dB bandwidth. 3 dB bandwidth is defined as the range of frequencies for which mod of H of b becomes 1 by root 2 times the maximum value of mod of HF, and this is the most commonly used definition of bandwidth that is adopted in measurement instruments or the function generators. So, let us try to understand this 3 dB bandwidth with a common example from electrical circuit world. So, here we have the example of RC circuit. So, you must have seen that the frequency response of an RC circuit is given by 1 upon 1 plus j 2 pi RC f. If I find the mod of this frequency response, it can be easily obtained by this expression. Okay. Now, what is the maximum value of this mod of HF? You can easily see that this will have the maximum value when this denominator achieves the smallest value, and this will be the case when f is 0, and hence the maximum value of mod of HF is 1. So, that is what we have here. The maximum value of mod of HF is 1, and thus we want B for which mod of H B is 1 by root 2. Now, substituting the mod of H B in this expression, we can find out the value of B. This should be B. From this we can find out the value of B, which will turn out to be 1 by 2 pi R C, and hence the 3 dB bandwidth for an RC circuit is 1 by 2 pi R C. There is a last definition that we have to look into, and that is the peak to first null bandwidth. So, I have plotted the mod of HF to our good old pulse, sync pulse, and if you look this definition of bandwidth, what it implies in here is you have to take the difference between the first null and the peak position, and this difference is very conveniently obtained, and this is 1 by T. So, if I consider the bandwidth of the sync pulse based on this idea of peak to first null bandwidth, the bandwidth of the sync pulse becomes 1 by T. So, there are different definitions of bandwidth that we have considered. We have looked into the fractional containment bandwidth, we have looked into the equivalent rectangular bandwidth, peak to first null bandwidth, 3 dB bandwidth, and not surprisingly that these different definitions of bandwidth have given us different results, and thus the choice of definition of bandwidth depends upon its context. Lastly, we have to look at the capacity, which illustrates why this bandwidth is so important. So, if you look at the capacity of a communication system, which is in bits per second, so how fast your internet can be depends upon this factor. This capacity is proportional to B, where B is the bandwidth of the communication system log 2 times 1 plus signal to noise ratio. So, SNR represents signal to noise ratio, and this is signal power divided by noise power, and this expression came from Shannon's celebrated work on communication system. Essentially, it says that you can increase the capacity by either increasing the bandwidth of the communication system or by increasing the signal power. Now, thus to want a higher capacity, we want to have a larger bandwidth, and this bandwidth is thus very important. Let us look at what are the typical numbers for bandwidth and signal to noise ratio for a telephone system. So, the bandwidth of a telephone system is restricted to this 4 kilohertz, signal to noise ratio is typically around 30 dB, and thus you can find that the capacity of a telephone system is around 40 kbps. So, when communication system started, people were trying to make communication systems which can achieve this theoretical value of capacity. This is a theoretical value of capacity, meaning that this is the best that you can have. A communication system's capacity is upper bounded by this value of C. So, when you are designing a communication system, your objective is to reach to this value of upper bound of the capacity that is given by the Shannon's equation. So, with this we have completed this unit and this lecture. In this lecture today, we have learned about what is the bandwidth, degree of freedom, and we have also seen T spaced sync weighted sinusoid expansion. In the next unit, we will start by looking into noise, because as you can see that the capacity and the performance of a system depends upon this noise power, and hence it is very important to understand what noise is and what are the typical values of noise power. So, we will start with this in unit 2 from next lectures.